Okay. All right. So is the microphone working? Yeah. All right. Yeah. Good morning, everyone. I feel honored. Like this is first in-person, GPU workshop, and I also miss like the cold weather, the snow. Having lived in Florida for 5 years, there's no much difference between winter and summer and fall and etc. They're all the same. But anyway, so today I will share our perspectives and my current and recent research on providing trusted execution environment on GPUs. And thank you for the introduction, Daniel. So let's kind of look into this. All right. So first of all, TEE in the cloud, right? So TEE is now very useful and used heavily in the cloud, and it basically provides several guarantees. So as a user of cloud computing, I want to send my data and my computation to the cloud, and then I want to receive the result of that computation. And what I want from the cloud is to have some guarantee of confidentiality of my data, the program, and the output of the program, right? So A, FX, F, and FA. And I want to make sure that also my program doesn't change. This is going to be just executing the thing that I upload and nothing more or less. And I want to be assured that I get the correct computation output, computation result from the cloud. Now, when I first worked on secure processor back in 2003 to 2006 timeframe, that's when I started my first research project. That was not really the goal of a secure processor. It was initially, I think, I remember the first paper was from Stanford. It was XOM, and it was designed to enable secure software distribution. But only after a few years, then people realized that, hey, this is useful for the cloud. So TEE is important, and I believe it will increase in its importance in the future. So it provides, it enables privacy-preserving computation in the cloud. Now, on that front, it's not the only technology that guarantees privacy-preserving, right? So you have like a bunch of other techniques, including homomorphic encryption, but they are all really expensive, and then TEE is kind of like the cheapest in terms of overheads. And it also like is good for the cloud providers to to basically approach the clients and say, hey, we have this technology that we use, so if you use it, you have certain guarantee by the hardware, and you don't even have to trust our system software, right? So it soothes clients' fear of data breaches in the cloud. And this may be a kind of like me, rubbing my crystal ball. Probably in my thought, it may be regulatorily required in the future, right? So if people start talking about confidential computing in the cloud, this could be, at some point, TEE may be required for that kind of use case. But this is just a prediction, okay? And many processors already provide TEEs, such as AMD SEV, Intel SGX was the first one, MKTME, ARM Trust Zone, etc. Now, however, in this community, this workshop attendees, you already know very well that GPU is rising in importance in the cloud. It's being used more and more, and it's kind of like mind-boggling to me that it becomes like the revenue from data center for NVIDIA, it starts to approach and may even exceed in the future revenue from games, from gaming console and etc. Right? So definitely the GPU is becoming like a really important compute platform in a cloud. But there is one problem, right? So GPUs currently have no TEE support. And that's a problem because, if I want to run some computation, and that computation, let's say, has a lot of parallelism, let's say machine learning, a deep neural network, etc. I don't want to run it on the CPU. I want to run it on the GPU and benefit from the parallelism. But if I choose the GPU, I cannot have the confidentiality integrity guarantee that I have with the CPU TE, right? So with that realization, I thought that maybe it's good to kind of revisit, how can we support TE on GPUs? So first, let's look at the threat model. Let's kind of look at what CPU assumes for threat model and trust model. So this is the trust model of CPU TE. So we trust the CPU chip. This is where everything that is security critical are placed, including the secret keys, integrity tree root, etc. It's placed in the CPU chip. So that forms the trust boundary. And with the assumption that, if you want to kind of attack something outside the CPU chip, is much easier than, removing the packaging and kind of like probe into the transistor, etc. So that's the core model. And then the threat model that is being assumed is basically two things. One is the compromised system software. So, for example, we assume that the attacker may be able to get control of the operating system and hypervisor. So I still want to run my application in the cloud, but I don't trust the operating system, don't trust the hypervisor. So I want the hardware instead to give me a secure enclave where my application runs. And then the second threat model is physical attacks. So the physical attacks may include someone kind of like plugging in some logic analyzer between the CPU and memory chip and kind of read the communication between chips. So you can do memory scanning, bus snooping, and may even be able to change values in memory. It could be through buffer overflow, the operating system, or it could be using like more sophisticated, techniques, maybe rowhammer, etc. Right? So basically, we assume that there is some possibility of the memory values to be tampered. And based on this threat model and the trust model, this is what architecture features that are provided by TEE. And in particular, this is the one that Intel SGX provided. So first is that they provide secure key storage and management in the CPU, and then attestation. Attestation is basically a way for you to kind of upload your code and data into an enclave, and then perform a secure measurement. And then that measurement is checked against an attestation server to basically certify the initial state of the enclave. Now, that kind of gives the guarantee that you start off with a good program and data state. After attestation happens, something else have to take control and to guarantee confidentiality, integrity, and etc. So here, this is the role. Basically, the attestation hands it off to the secure memory engine, right? So I call this SME. The SME has the following roles. The first one is it has to ensure confidentiality of any data stored off-chip. So that includes the main memory, as well as in swap space or storage, etc. And integrity. So it protects the integrity of data that is stored off-chip. So as long as the data is stored off-chip, when it brings it back into the processor, you want to be assured that nothing has changed to this data. And the last one is freshness. So, okay. So freshness is basically a feature in which we know that not only the data is valid, but the data is the same one I saw last, right? So the attacker doesn't roll it back. So out of these three features, key management, attestation, and memory engine, the one that is the most expensive in terms of performance overheads is the memory engine. Okay, why? Because it has to work on at the granularity of loads and stores, right? So you could have a cache miss, bring data, and that has to be protected. Whereas for the attestation, it's only done one time, right? Before you run your program, and then hardware key management only when you need it. So SME is the kind of like the most critical thing to optimize. And there is some prior work in this area, so including Graviton and HIGS. Graviton assumes a system software stack to be not trusted, and attackers will have physical access, and GPU management operations are offloaded rather than from GPU drivers, which is also untrusted, to the command processor, and then they assume that the PCI express bus is protected, and something similar with HIGS. Note, however, that none of this work assumes a secure memory engine or assumed memory encryption integrity verification. So basically, they work and they show pretty good performance overhead profile. However, it has not included the thing that is the most performance expensive, which is the memory encryption and integrity verification. So in this talk, I will briefly overview what recent work we have in this area. We tried to kind of answer several questions to get to the answer of TEE on GPU, right? So first question is that, what if we just take CPU TEE, a secure memory engine from CPU, and just put it on GPU? And what happened, right? So does it work? What kind of performance profiles we have, etc. The second thing is that, assuming that, let's say, it's not that optimal, performance optimal, so we are going to try to re-architect SME for GPUs to make it more GPU appropriate. So we're going to deal with some of the challenges. The next one is that, what opportunities that are specific to GPUs can be exploited to make SME fast? And the last one actually answers a question that is a bit different, meaning that, so if there is a GPU TEE, but then you also have CPU TEE, so how do you communicate between them, right? How do you pass data from CPU to GPU? So it turns out that you have to cross encryption domains, and that's kind of expensive, which we didn't anticipate earlier. Okay, so let's look at some of these questions. And so I'm going to try to go through a bit faster. Can we retrofit some CPU secure memory engine on GPUs, right? So what does the CPU use? Well, CPU use primarily like two types. So one is, the CPU could use a counter mode memory encryption, which is used in SGX, and then Bonsai-Merkle tree. Now, SGX doesn't use Bonsai-Merkle tree, but Bonsai-Merkle tree has been shown to be kind of like the smallest tree you can have. So that we're going to assume that, right? So in your encryption, basically what you encrypt is not the data itself, but you encrypt a seed that includes key, address, and counter. And so you encrypt that. All you need to do for transforming plain text to ciphertext of data is just XOR with this item or this pad. Okay. And the integrity tree only need to protect the counter, for some reason that, we have explained in our paper from 2007 or 2006. But basically, all you need to do is to ensure the integrity of the counter. You don't need to worry about MAC and data, and that's enough. Or you could use direct encryption mode and Merkle tree. So this is, for example, in AMD SEV, they use direct encryption mode. They don't use Merkle tree because they don't worry so much about integrity protection, or maybe because it is deemed to be too expensive. But basically, you encrypt directly the plaintext using the AES encryption or whatever encryption algorithm you want to have. And you protect the with the Merkle tree data and MAC. Actually, here is, it just shows MAC. Now, let's kind of put system like this on a GPU. So where do they go? Well, first of all, we assume the same trust model. So we trust the on-chip resource. So that basically covers the streaming multiprocessor, L1 cache and L2 cache, and the memory controller. So memory controller is kind of like the last place before data goes off chip. And therefore, that's where we integrate the memory encryption engine, right? So we add the encryption engine right here, and the MAC and hash engine right here, add some metadata cache. We note that the GPU organization, later this will become important. So GPU organization typically has partition memory. So meaning that you have a different memory controllers that don't talk to one another, okay? And they control different DRAM chips that also don't talk to one another. So this supports kind of like a high level of memory parallelism. And within this, there is a sector organization. Okay, so first we implement the counter mode on the GPU simulator, and the result is horrible, right? So it's like basically significant slowdown. So this is kind of like normalized IPC, assuming counter mode encryption and BMT. And you start off with perfect metadata cache that never misses, and then you start to introduce like more realistic scenarios, and the performance start to drop, and by a lot, right? So by 2/3 basically. And then we want to figure we try to figure out, okay, what is the reason for this? It turns out that the bandwidth, there's a substantial bandwidth pressure that increases because of the security metadata, right? So fetching the counter takes up some bandwidth, fetching the MAC uses bandwidth, Merkle tree uses bandwidth. So in the end, because bandwidth is like very precious in GPU, because of the nature of the workload, so this becomes like a performance bottleneck. And we can see from secondary miss as well. So if you have like streaming access pattern and sector data cache, this leads to high secondary miss, meaning that you have a miss on the same block again and again and again. Okay. So, and then we try unified versus separate metadata cache, right? So unified means we don't put metadata cache, but they just use the L2 cache along with data. Okay, so again, there's substantial, performance difference between unified versus separate cache. It turns out that it's because in GPU the dominant access pattern is streaming, and therefore streaming data kind of displaces the metadata, and therefore you kind of have to fetch it again and again. And counter mode encryption, because of the metadata caches, turns out to incur a die area that is quite significant. So it's like 25% of the 6 MB L2 cache. So we thought that, wow, what is the impact of that? So if we actually reduce the L2 cache size by about 25%, we try to measure its performance implication, but it turns out it did make a difference, but not as much. At least for this workloads right here that we try. Now, and then compare this with direct encryption. Okay, so it turns out with direct encryption you get rid of counters. You don't need counters, and therefore, if you just look at the encryption portion, actually the performance is so much better. Okay, and the reason why in CPU people chose the counter mode encryption is to avoid the latency so you fetch data and you still have to decrypt it, and that decryption could take tens of clock cycles, and that's very expensive. And in the CPU we use counter mode so that when data arrives you can do XOR to decrypt, which takes only 1 clock cycle. So that was a latency latency tolerant technique. But it turns out GPU, because of the parallelism, they don't benefit much from that latency reduction. They benefit more from bandwidth reduction. So in terms of confidentiality, if you use direct encryption, the performance overhead is very small. Now, however, this is where there is some problem. So if you use direct encryption and Merkle tree, now the Merkle tree is the one, a MAC and Merkle tree. So that's actually the one that reduced performance by a lot. Okay. Yeah. So that's kind of like the observations that we have. So there is no easy way to solve this. Basically, all of them incur large performance overhead, and that leads us to the second question, which is what are the challenges to re-architect SME for GPU? So let's look into deeper some of these questions. Let's revisit like the counter mode encryption, and in particular the split counter mode works this way. So you have physical memory with a bunch of blocks, and in order to encrypt or decrypt, you assemble counter, and a counter is basically a combination of a major counter concatenated with a per block counter, and that per block counter is called minor counter. Okay. So basically, for blocks that are part of a page, they share a major counter, but they have their own minor counter. And then we look at how do they map to GPU, right? So remember earlier I mentioned that GPU uses partition memory, and that turns out to be very relevant here, because suppose you have a memory interleaved in this way. So the dash line boundary describes basically a page, so 4 kilobytes, that gets interleaved in this way. So the first 2 blocks in first partition, the next 2 blocks in the second partition, etc. And this is understandably, for improving bandwidth, memory level parallelism. But once we use counter mode encryption and Bonsai Merkle tree, this organization actually hurts us. Okay, so for example, like if this is let's say we fetch all these blocks. So what happened is that we have to be able to decrypt these blocks, and to decrypt that we have to have a major counter, and we have to have a minor counter per block, right? So basically the same counter block, and this is like in one block you have like both the combination of major and minor. This block has to be fetched for every partition, right? Because the memory controller and they don't talk to one another. So each memory controller has to have access to this block. So the same counter block has to be accessed by all 32 partitions. That creates significant bandwidth pressure. And that will be the same story with Bonsai-Merkle tree nodes, because you have to verify the integrity of the counters, and you fetch the parent, etc. So it turns out that this is not ideal. So here we present the architecture that we start off with, that we want to optimize. So this just shows the partition memory with this SM, L1, and L2. Inside this memory controller, we add the memory encryption engine, metadata cache, and a root of the Merkle tree. So to address this, the problems that I mentioned earlier, we have to come up with something that is partition friendly for security metadata. So instead of spreading the or representing group of pages that are adjacent in physical memory, we're going to change the way what a counter block represents. So it will basically represent blocks that are within a partition, even though their physical addresses may be non-contiguous. And then we will reorganize the split counter block to make them more friendly to sector cache. Okay, so this is the picture from earlier. So you can see the physical address consists of these 32 blocks. But the counter, instead of one counter block representing them like this, we change the definition of the counter to use local address. Local address, basically the offset within a partition, rather than across partition, but in contiguous physical address. So the counter, basically now one counter block covers a group of blocks within a partition. So this way, only the first memory controller need to fetch that counter block. Other memory controllers don't need to. And then because of the cache is sector. Okay, so there's typically 4 sectors, and then also the counter block kind of scatter or spread out across sector. We try to make it fit into each sector. So then basically we change the format of the counter. Rather than having 64 bits counter block, 64-bit major counter, we use a smaller one so that each sector can have their own full counter. And for Mac bandwidth consumed by the Mac, we reduced the Mac size from 8 bytes to 4 bytes. Now this one is a bit tricky because I know this is like deals with the security strength of Mac protection. So our bet on this one is basically, most GPU applications will run on kernel that runs for a short amount of time. Okay, so by having like short-lived kernel rather than long-running application, it is possible to reduce the Mac, but of course it doesn't really fully provide the same full security. So by doing that, okay, so this is a bit too small, but let me just show basically the performance keeps on increasing the more we add the optimizations, right? So using the partition counter organization and then the sector organization, then we improve the performance. Yeah, you have a question?
Question.
Go ahead.
Okay, I was just wondering, when you shrink it from 8 bytes to 4 bytes.
Yeah.
Oh, sorry, my name is Trevor Carlson from NUS.
Yeah.
When you go from 8 bytes to 4 bytes, how long would that take? Because you said, okay, billion or 4 billion, right?
Right. Yeah.
What does that mean practically with respect to the time for collision? Because you're giving relative information.
Right.
It would be good to have more concrete.
Yeah. Yeah, I don't have the precise answer, but it's substantially reduced, right? So, and then the probability of collision increases substantially. So it's not an ideal solution. We tried it to see what is this performance, but in the next work we address that. So we get it back to 8 bytes.
About the security kind of, right?
Yeah.
Okay, thanks.
Thank you. All right, so let me just skip this one. So the next issue is that what opportunities do we have in re-architecting SME for GPUs? So in this case, we're gonna look at what is the nature of the GPU workload and the way GPU works, and see if we can actually, exploit these opportunities to improve SME performance. So the first observation is that GPU has heterogeneous memory, right? So it doesn't just have caches, it has scratch pad, it has texture memory, etc. So, given this, that the freshness protection actually is not really needed for all the types of memories. So if you have read-only space, you don't really need to protect its freshness. And not only that, some of the memories are located on chip as well. So here I'm showing you the types of memory GPU has and what kind of security protection it needs. So for example, local memory, we have to protect it fully. Global memory, the same thing. But constant memory and texture memory, this is actually, you don't really need to protect its freshness. And freshness is, by the way, is the most expensive part of SME because it requires a tree, right? So here, this is only needed, once in a while, right? Because it doesn't change all that frequently. So actually, when you run, you don't, this is constant as your kernel runs. And then shared memory is on chip, so no need for protection. So this is types of the memory. And then let's look at the GPU application itself. So type of data, right? So you can have the application code, and that's typically read-only. There's not a lot of cases in which application has to change while it runs. Maybe no cases. So there's the input and there's output, and typically the input is read-only, right? So it doesn't change either. The output is something that the kernel has to write, and then in-flight data can be read and written. So as you see here, that there's some part of this that you actually don't really need freshness protection. The second motivation is that CPU access pattern and GPU access pattern is quite different. Okay. So the GPU features a streaming data access pattern instead of random. So that means all memory blocks within a large memory chunk will be accessed together, or will be accessed in a consecutively. And MAC takes a significant overhead, right? So then this gives us opportunity to think about MAC at a larger granularity. So instead of MAC covering a block, now we can have a MAC covering an entire chunk in a streaming. So based on these observations, the key ideas of our solution is let's try to predict the data type. And we can start with assuming that everything is read-only until something happens, until you see a write, then you say, oh, my assumption was wrong. Now I have to treat it as read-write. And access pattern, whether it's streaming or non-streaming. So let's predict something streaming until something happens to invalidate that prediction. And then if, let's say, suppose that we are able to predict this with 100% accuracy, what is the opportunity we have for this? Well, if we have read-only data, right, we actually don't need an integrity tree. So you just use a counter, okay, to encrypt it. You use a counter that is shared by all read-only data, put it on chip, and never let it get out of chip. So then you don't have to worry about its freshness, and you don't have to worry about verifying the integrity of counters. Okay, so that's the opportunity with read-only data. What about if we see a streaming access pattern, right? So let's protect streaming with a MAC covering a chunk rather than block. So this can reduce MAC bandwidth overhead significantly. Now, I mentioned earlier, if we are accurate 100%, but prediction cannot be accurate 100%. So if we have a misprediction, we're going to deal with this by basically, oops, we fetch the data using the wrong counter. This counter is assuming that the data is read-only, so we basically just have to refetch the data and then fetch the correct counter, etc. Okay, so misprediction can happen, and the solution is not that it's not that difficult. We just need to refetch data. And yeah, so with these changes, you're gonna add a bunch of other things to the memory controller. So you have this tree from before, and then you have a shared counter for the read-only data, and you add one more, which is a predictor. So in the interest of time, I'm going to skip the details. So there's some, yeah. So I want to say something about the handling misprediction of read accesses. So here's when we predict that data is read-only, and this is prediction for access pattern, either streaming or random, and we could have accurate prediction. So when we detect it, it's also streaming, so we don't have to do anything about that. But it could be, we could be wrong, in this case, random, right? And so we already fetched the chunk MAC in this case, but it turns out that the access pattern is not streaming, instead it's random. So then we have fetched the wrong MAC. Okay, so then we have to refetch the block MAC, and then if it's like not read-only, then we have to refetch all the data blocks. So this is how, an example of how to handle misprediction. Yeah, so I will skip this, and the prediction doesn't take a lot of space. It's pretty simple because of the GPU simplicity. So try to simulate this using a GPU simulator, and a few things to show. read-only data prediction, then that our predictor, you don't need like complex predictor. Simple predictor does pretty well, so 89% accurate. In fact, it's accurate for most of the programs. Only some programs they are not so accurate. And the streaming pattern predictor is also pretty accurate, so 80+%. Okay. So performance comparison. So after we do all that prediction, okay, performance increases. So this normalized IPC again. So it kind of goes to about 90% of a system without memory encryption. Now, final question we try to answer is that should CPU and GPU TEE be co-designed? So here's the situation. So I think it's kind of difficult to really co-design CPU and GPU. They are independently designed. Typically, they are made by different vendors, although, in some case, maybe AMD, for example, produce both CPU and GPU, the same vendor, but they typically design with different constraints, different life cycle, different time frame. So it's kind of like difficult to co-design them, maybe challenging, maybe add to the cost of the chip design. So as a result, maybe what we should assume is that they are not co-designed. So in that case, they're going to form a different encryption domains. And then what we observe is that if they form different encryption domains, that means you cannot just do, like a simple mem copy from CPU to GPU. Okay. Now, here's, for example, you have a CPU with a TEE and GPU with its own TEE, and they are different TEE. So if you want to pass data from the CPU to the GPU, first you have to take data from the CPU encryption domain and then encrypt it with some software, with some software method, and then do a mem copy into the GPU domain, and then decrypt it with the same software method. And then after that is inside the encryption domain of the GPU, then you start using it. But look at how many encryption and decryption you have. And we know that the mem copy is kind of like a big overhead for GPU. It takes some effort to hide it, but now you have additional overhead from crossing encryption domain. And we measure that. And it turns out that even though, using all these, techniques, prediction, streaming, etc., we are able to kind of keep the memory encryption overhead small, but the re-encryption, crossing the encryption domain, actually incurs more overheads than just the GPU memory encryption. So our approach is basically to think about, well, what can we do about this? So can they be in the same domain but without having to co-design them? We are toying with an idea of, well, let's do the encryption in software for GPU. Okay, so the goal is to eliminate encryption domain crossing, and yeah, we use GPU TEE. So we design GPU TEE in software. It allows co-designing GPU to match that of CPU. Okay. And so this basically make the GPU encryption, memory encryption very flexible, and you can match it with what the CPU provides. Okay, so if you use different CPU, you can match it, you can deploy it with in software. How much more time do I have? About 10 minutes. Okay, so I'll go a bit faster. Yeah, so actually, oh yeah, maybe I should explain the diagram here. So if they GPU and CPU use the same encryption domain, you can just do simple memory copy. And then when you do decryption in software, this is what happens. So the data will be read into L2 cache, into L1 cache. And before they're used by the CPU, it will be brought into the shared memory. And at that time, we decrypt it, right? So they decrypt into the shared memory, and then it's used by the GPU. So it's a lot simpler because, you know, now you have to deal just with just one encryption domain, and then all you need to pay now is the overhead to decrypt from cache to shared memory. Now there's another unique feature of this, which is the data stay encrypted in the memory, in the cache hierarchy, basically. We think that there must be some advantage of this in terms of certain things. I don't know, maybe side channel or something, but we couldn't really conjure up an attack that, you know, that becomes impossible with this. So I just, you know, throw it out to the community, see if you can figure out something, some usefulness of this. So in terms of using this, so it's pretty simple, because basically you retain your GPU code, and then you just before you use it, you decrypt it. You put a decrypt function, and then you decrypt it. Yeah. So there are some challenges that we have to deal with. The thing is that mainly that encryption is 128-bit granularity. So in a block, you may have you know, 4 of these that you have to compute AES on. And so we need to look into the access pattern. So if the access pattern is streaming, then it's pretty simple, regular, right? So these are from different threads, but some applications will have irregular, and then you could have a branch, you know, divergence. So with different threads executing different things. Okay. So in that case, you cannot, for example, in this case, you cannot assume that all the, you know, all the data in a block will be used by all the threads. So to address this, basically we try to do a few things. For this one, we use a shuffle instruction to collect all this 128-bit quantity, so we can compute the the plain text, right? So we can decrypt it. And then for irregular data access, we perform padding. So basically we expand it. We expand the data, so the data becomes bigger. So this could quadruple memory access, and warp may suffer from thread divergent branch. So we apply some kind of optimizations. Basically, we, instead of shuffling after we perform the computation, now we use mask shuffling, and we change the timing of the shuffle, and we perform the selective padding. Okay, so it's evaluation setup. I skip that. So by doing that, it turns out the software encryption overhead can decrease from 19% to just 1%. So that's kind of negligible. And it's also nice in that you don't have to have metadata cache and all these things. It's a significant hardware structure that need to be verified, etc. This is all software. The problem is we have still is with the irregular application. So irregular application, after we do selective encryption, we still have a problem. You know, 206%, it decreases to 56%, but it's still high, right? So we don't have a solution yet to reduce this further. So that's where we stop. And then we can also further think about if encryption should be performed on everything. I think this is quite dependent on software characteristic. So which one is private data? So for example, If I want to do image recognition, maybe only the image is secret, right? Or needs confidentiality. So you can have input only encryption, or you can have output only encryption if only the output is confidential. And we don't know. This is up to the programmer, right? But if you are able to kind of selectively apply encryption, and this is what is nice about software, you can tailor this, the overhead can decrease significantly. So in conclusions, we find that GPU-TEE can be performed in software. It's great. It's flexible. Merge the encryption domain. It allows unified memory to work just fine without substantial overheads. Overheads are low for regular application with regular accesses, but it's still high for irregular accesses. Flexibility can be exploited. Like, for example, just encrypt input, only encrypt the output, or everything. All right, so that concludes our talk. I want to thank the PhD students, RD and Jake, and collaborators at NC State, Shogang, and two professors, Huyang and Amro. I'd be happy to answer your questions.
Do we have any questions? Very nice. So very nice talk.
Thank you.
So two quick questions. The first one is you started to talk about it at the very end, which is you have some you're trying to reduce the overhead when you're doing encryption on the GPU on the device, and that's great, but it's not free. And you're taking away resources because there are some games who basically have to devote extra hardware to that, the memory controller and other things that you're modifying. Have you considered how much you slow down the rest of the workload that doesn't need security?
Yeah, that's a good point. I think there are two components of that. So one is whether memory encryption and integrity verification should be turned on or not. So that one, I think you can apply a concept of enclave. So only application that request to run in an enclave should pay that overhead. But there's a second component of that, which is the die area that you use for all this encryption structure, metadata cache, etc. Applications that don't use that don't use this encryption will also suffer because they have a little bit smaller, L2 cache, etc. Right? And yeah, so I think definitely there is some overhead. In fact, earlier I showed some slides. If you reduce the L2 cache by up to 25%, what happens? So overhead, so there is some slowdown by a few percent. Not substantial for most applications, but it's there. I think in the end, the question is it worth to provide the security, a secure enclave on GPU or not? Because even with, even with CPU, right, memory encryption is, quite a substantial overhead. Yeah.
So my second question is, so this your counter-based protection is basically still susceptible to side channels, correct?
Yeah, we didn't address side channel. So yeah, there is always some side channel with TEE, unless you do something about, yeah.
So why not go to fully homomorphic decryption? I would support that on the GPU.
Yeah, that's a good question. So actually, homomorphic.
You do this encryption, you just compute.
Right. Yeah, we have run some preliminary experiments with full homomorphic encryption. It's still really slow right now, right? So you still have about 1,000 to 10,000x slowdown.
Getting better.
It's getting better, but it's, you know, the overhead is kind of like on a different level.
scale, but
Yeah,
it's
different
getting-
scale.
It's getting really.
With homomorphic encryption, though, you can so basically, if you want to remove sidechain, for example, you have to perform cache partitioning or bandwidth partitioning, and you have to turn off speculation on CPU. On GPU, I don't know what else. Maybe coalescing needs to be turned off. So basically, there's quite some overheads that you don't have to. You can get rid of if you use homomorphic. So I think it closes some gap, but it's still like on a different level. Yeah.
Thank you.
But yeah, thanks. That's actually, by the way, that's a very interesting question. I think this should more people should work on that. Yeah.
Any other questions? Okay, I have a question.
Yeah.
Can I use the mic? I have a quick question. So there's multi-GPU systems now where GPUs can access the memory of other GPUs. Would that introduce any kind of cross encryption domain couple optimization or other challenges?
Yeah. So yes, that presents new challenges. Basically, where do you assume you maintain the key, right? So I think the problem is similar to SGX version 1 in CPU versus SGX version 2. So in version 1, they assume basically just one processor chip. And then once you want to scale, run bigger programs that cross multiple CPU chips, you have to provide secure communication across the CPUs. So you can do kind of like encrypted communication and integrity verified communication, etc. I think the same will apply to multiple GPUs. So you have to kind of have that kind of protection. Let me see what may be unique to GPUs. Yeah, I'm sure the way that encrypted is designed to hide the latency of this communication, considering the GPU's access pattern, there may be some interesting, question